Well, hello, ladies and gentlemen. So today we're going to move on from our analysis of entropy, and we're going to move moving on to applications of what we've learned about entropy and energy into analyzing work-producing devices. In particular, we're going to start off with closed system work-producing devices. These are piston cylinder devices, just like the Carnot cycle. So we're going to start off analyzing piston cylinder devices, and then we're going to move on to open system devices, like jet engines and gas turbines. Open system devices, we're going to analyze open system work-producing devices. We'll be doing that next week, but we're going to start off with closed system work-producing devices, similar to what you have in your car, whether it's a gasoline or a diesel engine. So we're going to be investigating how we can produce power using a closed system cyclic device. And we're going to incorporate all the tools, all the things we've learned about energy and entropy to do it. So topics here: gas power cycle. That's what we're going to be doing for the next couple of weeks. We're going to start off with closed systems, and then we're going to move to open systems. Today we're going to begin by reviewing the Carnot cycle, make sure that we remember and review a little bit about how the Carnot cycle works, because we're going to take the Carnot cycle, we're going to take the piston cylinder device, and we're going to add heat or reject heat or compress it, compress the air or the gas. We're going to do this in all different ways and try to figure out what the efficiency is and the power output is, depending on the various processes that make up the cycle. So we're going to review the Carnot cycle. Then we're going to discuss for a moment why we don't build Carnot cycles in real life. It's not really anything to do with excluding friction or unrestrained expansion. There's more deeper problems. There's some deeper engineering problems or reasons why we don't try to build Carnot cycles. So we're going to talk about why the Carnot cycle isn't practical, and we can't even attempt to build anything near a Carnot cycle, and I'll tell you why in just a moment. So as a result, we're stuck with less efficient cycles that are similar but not quite the same to the Carnot cycle. So we're going to talk about these additional cycles and therefore the cycle analysis as we go along for the next week or two. We're going to analyze these other cycles using what's called the air standard cycle analysis. It's a set of assumptions that make blackboard work and analysis of closed system cycles relatively easy and straightforward. There's a lot of things going on in a work-producing device, a physical work-producing device, but we can get a lot of analytical and analysis mileage out of the work that we do on the blackboard by making some simplifying assumptions. So there's a bunch of simplifying assumptions we're going to make for this air standard cycle analysis stuff. We're also going to investigate the implication of internal versus external irreversibilities. So there's a question about, remember, the Carnot cycle is reversible. So the Carnot cycle doesn't result in any entropy generation. It's a completely reversible cycle. The cycles we're going to look at today are not reversible cycles. They have irreversibilities occurring somewhere. And so we need to talk about internal versus external irreversibilities. Then we're going to look at how the energy and entropy balance is reduced when we're dealing with this cycle analysis stuff. And then we're going to take the energy and entropy balances and we're going to use them to analyze the efficiency and power produced by various closed system cycles. We're going to do this using graphical analysis. Remember on the PV diagram, the area bound by the PV curve is the boundary work. Well, you can do similar stuff with the temperature entropy plot. You can represent heat transfers and net work using the TS diagram. So we're going to talk about interpretation of the cycle on the TS diagram and how we can extract efficiency and work graphically using the TS diagram. And then if we have time, we'll begin and maybe complete, if we're lucky, a numerical example of some cycle analysis. Okay, we're going to analyze a particular cycle numerically, just like we did previously when we analyzed the Carnot refrigerator, as I recall. We'll do the same thing with some other cycle, okay? Some other cycle. Now let's have a look here. Let's go review the Carnot cycle here. So the Carnot cycle was composed of two isothermal heat interactions and two adiabatic expansion or compression processes. So in particular, we started off at state 1. So this is the PV diagram and this is the TS diagram right here. We start off with state 1, which is the minimum pressure. Maximum pressure and minimum volume point. So state 1 is where we squeeze the gas down. State 1 is at the high temperature reservoir temperature TH. So at state 1, we're at temperature T high and we are at the minimum volume. And then we proceed to expand isothermally the gas in our piston cylinder device, and we do it reversibly. No friction, no unrestrained expansion. Unrestrained expansion means it happens very slowly. Happens very slowly. So we expand the gas isothermally. Pressure falls, volume goes up. On the PV diagram, we're expanding it isothermally. Entropy is being brought into the system, the air, the gas, or whatever it is, the working fluid. So if entropy is being brought into the system, that means entropy goes up. So as we go from state 1 to state 2, entropy goes up, temperature remains constant. So that's indicated on the TS diagram. And then from process 2 to 3, we wrap the piston cylinder device in some kind of insulation. No heat transfer. And then we expand the gas down to the low temperature, reservoir temperature TL. So 2 to 3 is adiabatic. Now remember, the Carnot cycle is reversible, so there's no S-gen. If it's adiabatic and there's no entropy generation, that means it's isentropic. So remember, the entropy balance, delta S for a closed system is equal to the integral of del Q over T plus S-gen. So if there's no generation, entropy generation, and no heat transfer, delta S is 0. So process 2 to 3, which is adiabatic expansion, reversible expansion, is an isentropic process. So from 2 to 3, we go vertically down to the low temperature TL, okay? So we isentropically expand the gas down to temperature TL. Once we get to the low temperature reservoir temperature TL, we then proceed to compress the gas and reject the excess heat, QL, from the working fluid to the low temperature reservoir. Okay? And then to get back to state 1, well, to get back to state 1, we simply compress adiabatically and reversibly, compress the fluid back up to the high temperature state. And that gets us back to state 1, okay? So 2 isothermal, 4 to 1, 1 to 2, 1 to 2, and then 3 to 4. These are both isothermal processes. And then 2 adiabatic expansion or compression processes make up the Carnot cycle. No friction, no unrestrained expansion. And that means that the process is very slow. We don't want the piston being jerked up and down. That would be unrestrained expansion or irreversible compression. So the process is really slow. And then we don't want any heat transfer across a finite temperature difference. That means that the heat transfer must occur at the high temperature and the low temperature reservoir temperatures. So in theory, the Carnot cycle is reversible. Okay, reversible. Now, why don't we build Carnot cycles? Why don't we actually build them? After all, the maximum efficiency, the most efficient cycle, is a Carnot cycle because it's reversible. So remember the restrictions here on reversibility. So the Carnot cycle has to be reversible. That means no friction, no unrestrained expansion, and no heat transfer across a finite temperature difference. So let's talk about these restrictions for a moment. Let's just talk about these restrictions here for a moment. So Carnot cycle. So it's reversible. It's reversible. And what does that mean? That means no friction. No unrestrained expansion. And then we have no heat transfer across a finite delta T. No heat transfer across a delta T, a finite delta T, okay? So let's talk about these for a moment. If we wanted to build a Carnot device, a cycle, a physical device based on the Carnot cycle, how would we implement, if we could implement, any of these restrictions associated with the reversibility of the cycle? Well, no friction. What can we do about no friction? Well, we can make sure we use good oils, lots of lubrication. So this piston and this cylinder, okay, there's going to be friction in between the piston and the cylinder. So here's a piston wall and here's a cylinder wall. So we would need good lubrication, in theory, perfect lubrication. You also need good machining, okay? Good machining to reduce friction. You don't want a bunch of rough internal surfaces, machine surfaces inside your piston cylinder device. So to achieve minimal friction, so we're going to try to achieve, we can minimize friction. We can minimize friction by using lubrication. And good machining. Good machining of parts. Okay, the better machined and manufactured your parts, the less friction there's going to be. And the better your oils that you use to lubricate, of course, the lower the friction is going to be. So we can approach the Carnot cycle by having well-machined piston cylinder devices using lubrication. So that's how we can address the no friction. That's how we can approach the Carnot cycle physically, is by minimizing friction using good machining and good lubricants. What about this no unrestrained expansion? Well, we can approach or minimize the presence of unrestrained expansion by having the piston cylinder device work very slowly. Remember, the faster the piston goes up and down. So unrestrained expansion is caused by the piston jerking up and down so quickly that the gas doesn't have a chance to move along with the piston, forming a low pressure or perhaps a partial vacuum near the piston. Remember, unrestrained expansion is irreversible, so we want the piston to move slowly. So what we have here is slow operation. How slow is slow? Well, we want the piston speed to be much less than the speed of sound. So piston speed, slow operation, piston speed, much, much less than the speed of sound. Speed of sound is the speed in which a pressure wave propagates through a gas. And pressure is how a gas responds. A gas responds due to the movement of a surface due to a pressure wave. So if the pressure wave can't keep up with the piston, you're going to get some kind of unrestrained expansion. So piston speed, much, much less than the speed of sound. So that's a way we could have slow turning piston cylinder devices or engines, and that would minimize the presence of unrestrained expansion. By the way, for those of you that are big diesel fans, you have a diesel truck, big diesels tend to turn or operate at a very low RPM. So that is one reason why diesels are very efficient. One possible reason why diesels are very efficient, they tend to turn very slowly, therefore minimizing unrestrained expansion. So that's one benefit of a slow turning, especially a slow turning diesel, okay? Now, the last one here, no heat transfer across a finite delta T. That's the one where we get into trouble when we try to envision how we could build a physical, practical, commercially available Carnot cycle. This is the one that is difficult or basically impossible to implement. No heat transfer across a finite temperature difference. What this really means is we have to minimize temperature differences during the heat transfer process. So min delta T for heat transfer processes. Now, this is a problem. I'll tell you why it's a problem. Let's say, for example, we are transferring heat in our Carnot cycle. So we have our high temperature reservoir and we have our Carnot heat engine. And our Carnot heat engine is composed of a piston cylinder device. So here's my piston cylinder device, okay? Now I'm trying to transfer heat into my working fluid, okay? And my working fluid has a temperature, if it's a Carnot cycle, it would have a temperature T high. So this is a Carnot cycle. This is the Carnot cycle. When the cycle is receiving the high temperature heat addition, the working fluid needs to be at a temperature T high. If the temperature is not T high in the working fluid, then we have a temperature difference delta T between the reservoir and the working fluid, and it wouldn't be reversible. So the Carnot cycle transfers heat from the high temperature reservoir at a temperature T high. Now there's a problem here. As you may have noticed in your homework assignment and in the exam, you saw an expression at some point giving the rate of heat transfer. So Q dot typically is equal to some kind of constant C. The rate of heat transfer between objects is usually a constant C times a delta T. So we have an object here. So we got T1 and we got T2. Heat transfers from T1 to T2 due to a temperature difference. So this delta T here might be T1 minus T2. I guess maybe I'll make this A and B. How about that? Two different systems. One system is at temperature A and the other system is at temperature B. And my delta T is TA minus TB. So the rate of heat transfer, Q dot, is equal to a temperature difference between the two systems. If the temperatures of these two systems are the same, delta T is 0 and we get no heat transfer. So delta T equals 0, no heat transfer. As delta T goes up, so this becomes much hotter than this is cool, heat transfer increases. So as the temperature difference, delta T, goes up, the rate of heat transfer goes up. So heat transfer is proportional to the temperature difference between systems. That's typically how it works in real life. Q dot is proportional to a temperature difference between systems. Now, in the Carnot cycle, the reservoir temperature and the working fluid temperature during the heat addition process are the same. They are both at temperature T high. So during the heat addition process, for example, so note for the Carnot cycle, during the heat addition process, 1 to 2, which is isothermal heat addition at temperature equals T high. So process 1 to 2, the temperature of the working fluid is at a temperature T high, which is our high temperature reservoir temperature. According to this, delta T is equal to 0 and Q dot is equal to 0. So in theory, if we transfer heat from the high temperature reservoir into the working fluid and the working fluid is at the same temperature, in theory, Q dot, or the rate of heat transfer, is 0. So in reality, process 1 to 2 or any heat interaction for the Carnot cycle is reversible, but it results in a 0 rate of heat transfer. We actually don't get any heat transfer if we try to build this thing. So the heat interactions occur at the reservoir temperatures. That means delta T is 0 between the reservoir and the working fluid. That means in theory the rate of heat transfers are 0. Heat transfer rate is approximately 0 for the Carnot cycle. The Carnot cycle transfers heat at basically a 0 rate. The rate of heat transfer from the high to the low temperature reservoir and the rate of work produced is approximately 0 kilowatts. It's the most efficient cycle. It has the highest efficiency, but it also produces 0 power. Power is work per unit time. Heat transfer is approximately 0. Therefore, W dot is approximately 0. No power. The Carnot cycle is very efficient, but if we try to build one, it will produce 0 power, approximately. So the Carnot cycle is not a very practical heat engine to build, not because we can't minimize friction, not because we can't minimize unrestrained expansion, but because the heat transfer rate is so low to the working fluid that we can't produce any power. Your highly efficient Carnot heat engine has 0 horsepower output. That's not good. That's not going to sell many cars. The Carnot experience, 0 to 60 in a lifetime. That's not good. Not good at all. Okay, so the Carnot cycle is out. We can't build it. It's not practical. So why don't we relax one of our assumptions? Let's not relax the frictionless behavior. Let's not relax the no friction. Let's not relax the unrestrained expansion. But let's relax the third constraint. No heat transfer across a finite temperature difference. let's relax the last constraint on our cycle. It's going to be irreversible, but let's relax the last constraint. So relax last constraint. In other words, we allow heat transfer across a finite delta T. Okay? We're going to allow our heat engine, which interacts between some temperature limits. So here's our heat engine. Here's T high and here's T low. We're going to allow it to receive heat or reject heat. We're going to allow it to receive heat or reject heat. Where the working fluid is at some temperature T, where T is less than, well, T is not equal to T high or T low. T high or T low. We're going to let T of the working fluid be different than T high or T low when we have heat interactions. Okay? We're going to allow heat transfer across a finite delta T. That means that, so here's our system right here. So there's a temperature right here, T, whatever that is. So there's our temperature T. The idea is we have a temperature difference between the high temperature reservoir and the low temperature reservoir. We might have a delta T, which is TH minus T, and it might be finite. So there might be a temperature difference between where the heat flows from the high temperature reservoir into where it flows into our system. There might be a finite delta T. That means outside of my system, there's irreversibility. And the irreversibility takes place in this region between the high temperature reservoir and my system, my piston cylinder device. So in this region right here, between the reservoirs and my system, in this region there are irreversibilities. Irreversibilities present. In other words, the cycle that we're going to analyze is internally reversible. There's no irreversibilities going on inside, but there are external irreversibilities. There's irreversibilities occurring between the source of the heat, which is the high or the low temperature reservoir, and where it interacts with the system, which is at a temperature T. So we're going to allow for external irreversibility in our cycle, but not internal irreversibility within our cycle. And we do that so we can actually get some heat transfer. We want a delta T here, a finite delta T. In fact, the greater the delta T, the more the heat gets transferred per unit time and the more power we produce. Okay? All right, so let's list the assumptions for our cycle analysis. Let's list the assumptions for our cycle analysis. So, air standard cycle analysis. Air standard cycle analysis. Let's write the assumptions here. So we have air is the working fluid. Air is system, or if you like, working fluid. So air is the working fluid. Let me make sure I have all these assumptions. There's quite a few, and I don't want to miss any of them. Let's see here. Air is the working fluid. We're going to start off with a closed system. We'll relax this and go to open system cycle analysis in a minute. Closed system, so we're going to start off with piston, cylinder, device, okay? We are going to have internally reversible, process. What I mean by that is no friction, unrestrained expansion, or heat transfer across a delta T inside my system. So we have our piston cylinder device right here. Here it is right here. Here's our piston cylinder device. And so the piston goes up and down. Our system is the air. There's no friction inside of here. No unrestrained expansion and no heat transfer inside my system over a temperature difference. We can have heat transfer across a temperature difference outside the system. In other words, between the piston cylinder device and wherever it receives or rejects heat from or to. We can definitely have a delta T between the reservoirs and the system temperature when we have heat transfer, but there can't be any temperature variations inside the system resulting in any heat transfer, okay? Temperature is always uniform, spatially uniform inside of my system. We're also going to neglect changes in kinetic and potential energy. Delta PE equals delta KE, and they're equal to 0. So there's no, we're not going to take into account in our analysis any changes in position of the gas or any movement of the gas kinetic energy. We're also going to assume that all work is boundary work, hence it's a piston cylinder device. So work equals work boundary. Okay? Now, real devices, the internal combustion engine in your car, the Otto cycle or the diesel cycle, use the burning of air and fuel to produce heat. We're going to replace the combustion, the burning process, with a simple heat transfer process. Instead of burning, modeling the burning of diesel or gasoline inside of the piston cylinder device, releasing heat, we're going to say that it's a simple heat transfer process from a high temperature location or a heat rejection process to a low temperature location. So we're going to look at heat transfers replacing combustion processes, okay? So I'm going to write here, Q low and Q high replace combustion process or rejection or exhausting of the products of combustion, okay? Maybe before we proceed a little bit further, why don't we actually go over, let me just make sure everybody's on the same page. Let's go over a simple process, an idealized gasoline or diesel engine, so we can discuss how it works here very quickly and make sure everybody's on the same page. So let's go to the notes here. You go to the chapter 7 on gas. We'll talk about vapor power cycles. We're going to deal with ideal gas. Oh, I forgot to put it on the list here, but ideal gas behavior, I'll put that up in just a moment. We're going to assume ideal gas behavior for all of our analysis as well. So let's look at an actual internal combustion engine device and how it might work. So imagine that we have here in a piston cylinder device. So here's the walls of the piston. Here, I'm sorry, the cylinder, and here's a piston which moves up and down inside of the cylinder. There's a connecting rod here connected to a crankshaft, and the crankshaft spins around. So we start off with air-fuel mixture at the maximum volume state, and then we proceed to compress. We proceed to compress the air-fuel mixture to a minimum volume. So we squeeze it down, temperature goes up, volume goes down, and then we initiate the combustion process. This air-fuel mixture starts to burn. Either we have a spark or the mixture starts burning on its own due to the excessive heat, whatever. So we start off with an air-fuel mixture, we compress it, we initiate a spark with a spark plug, and then all of a sudden, heat gets released due to the burning of the air-fuel mixture. Now, the piston moves downward under the expanding hot gases due to the heat being released, and that tends to drive the piston down, producing power. Once the piston gets down all the way to the bottom of its stroke, this is called top dead center, by the way, top dead center where the piston is at the top of the stroke. And then at the bottom, we are at bottom dead center. The air-fuel mixture is now burnt, and we have the products of combustion. That would be carbon dioxide, water vapor. So when we get down to the bottom of the stroke, a little valve called the exhaust valve opens up, and the hot, burnt air-fuel mixture, the products of combustion, starts to rush out the exhaust port through the exhaust system out of the tailpipe. Now the piston moves upward to top dead center one more time, pushing out all the burnt air-fuel mixture, the products of combustion. And then an intake valve opens up, the exhaust valve closes, an intake valve opens up, the piston moves downward, pulling in fresh air-fuel mixture unburnt, and then we end up back here at state 1, ready to repeat the cycle, okay? So this is called a two-stroke or a two-revolution. It requires 2 revolutions of the crankcase to complete a cycle. It's called a two-stroke internal combustion engine cycle. We have the burning of the fuel, which releases heat, so that's our Q dot I, coming into our working fluid, if you like. And then once the fuel is burned and is expanded to produce the power, the burnt fuel is replaced with fresh air fuel by opening up an exhaust valve, pushing out the burnt fuel, air-fuel mixture, and opening up an intake valve and taking in fresh air fuel. So we're going to replace this bottom process here, where we reject or expel the burnt fuel and intake fresh fuel. We're going to model that as a simple heat rejection process. Okay? The heat addition process replaces the burning of the fuel. That's the Q dot high. And the heat rejection processes replaces the expelling of burnt air fuel mixture and intake of fresh air fuel mixture. Okay? So we're replacing the combustion process and the replacement of burnt air fuel mixture with simple heat transfers, QL and QH. Okay? And also, I didn't put it down here, but I'm going to write right here ideal gas behavior, IGB, ideal gas behavior, we're going to assume for the working fluid. Okay? All right, let's take a break for a second here. Let's take a pause. We'll go on to some more material. Okay, let's say we have a cyclic device. It's a heat engine extracting heat from some high temperature reservoir and rejecting heat to a low temperature reservoir. This thing operates in a cycle, so it produces work, W cycle. So let's analyze this cycle using the energy balance and the entropy balance and see what we get. So how about the E balance? So let's apply the E balance to our cyclic heat engine. So I'm going to write the energy balance and I'm going to apply it over the cycle. So I'm going to write here Q over the cycle minus the work produced over the cycle is equal to delta E over the cycle. Delta E over the cycle. Now, over a cycle, there are no changes in any properties. So the change in energy over the cycle is 0. That goes away. So what that says is that the work produced by the cyclic device, is equal to the heat added over the cycle. This is a net heat or total heat added over the cycle. Now, heat is brought in and then rejected. So Q cycle is actually Q high, which is being added to the system, minus QL, which is being rejected by the system. So W cycle is equal to QH minus QL. So W cycle is equal to the heat over the cycle, which is equal to Q high minus Q low, or Q in minus Q out. If you want to put an in and an out here instead of a high or a low, that's fine with me. That's fine with me. Okay? What about the entropy balance? So let's put a little box around this. What about the entropy balance? S balance. Okay? Now, first of all, I'm going to write the differential form of the closed system entropy balance. So remember, we have ds is equal to del Q over T interaction plus del S gen. Now, for our cycle analysis stuff, our air standard cycle analysis, one of the assumptions is internally reversible. There's no irreversible processes going on in here. So that means there's no entropy being generated. So I'm going to put a 0 here. So I'm going to write internally reversible. Internally reversible. Okay? No entropy generation inside my heat engine. Now, one consequence of that is, so let me draw a picture of the piston cylinder device containing my working fluid. So here's my working fluid right here. So here's my gas. Now, let's say somewhere inside the system, the temperatures were different. Let's say we have a temperature over here, I don't know, T, and then over here I have T plus a delta T. So it's cool over here and warm over here. So cold and warm. What's going to happen to heat transfer inside my gas, where I have a cold side and a warm side? Well, heat is going to get transferred from hot to cold. In fact, that's heat transfer across a finite temperature difference, delta T. I can't have that. Why? Because inside the system, there's no irreversibilities. So what that means is the temperature inside of my gas cannot vary spatially. There can't be a cold part and a warm part. It all has to be the same temperature inside, or I get heat transfer across a finite temperature difference inside my system. That means that the interaction temperature, or the temperature that I measure anywhere on the surface of my system, anywhere, the interaction temperature where the heat crosses the system boundary has to be equal to the gas temperature. There has to be a uniform temperature, spatially uniform. Temperature is the same everywhere inside my gas. So this temperature is not an interaction temperature, it's just the plain old temperature of my gas, T, okay? So no delta T inside. This implies temp is a uniform T. Temperature within my air, my gas, my working fluid is uniform everywhere. It's at a temperature T. T is the temperature of the gas. So I get ds is equal to del Q over T. Okay? Now I'm going to solve that for the heat transfer. Multiply both sides by temperature T, flip the equation, and I get del Q, I'll do it down here, and I get del Q is equal to T ds. Okay, internally reversible, that's what I have to have. That's what I have to have. Now let's integrate this over the cycle. Let's integrate this over the cycle. The heat transfer integrated over the cycle is my Q cycle. Q cycle, which by the way is equal to my work. Work cycle, okay? So what this means is work of the cycle is equal to Q of the cycle, which is equal to the integral over the cycle of temperature ds. Put a box around that. The cycle work for our internally reversible piston cylinder device closed system, the cycle work is equal to the integral of TDS. What does that mean? That means if I plot my cycle, on the temperature entropy plot, TS, here's my cycle. There's my cycle, just a circle, let's say. The area bound by the TS curve. The area bound by the TS curve is the heat added over the cycle, which is the work produced over the cycle. So this area in here represents my cycle work. W cycle. That's nice because remember the area bound by the PV curve was the boundary work. Remember the area bound by the PV curve was the boundary work. or the cycle work, because the work is boundary work. So we have similar interpretations of the area bound by the PV curve and the TS curve for our cycle analysis assumptions. The area bound by the TS curve is the work over the cycle, or the net heat transfer, or cycle heat transfer, Q high minus Q low. Okay? Now, before we move on, I want to point out one more thing about the entropy balance. Not only can I calculate the cycle work, by getting the area bound by the TS curve for the cycle, I can get the heat addition and the heat rejection too. So let me write this here. So recall, del Q is equal to TdS. That means the heat transfer over some process, 1 to 2, is equal to the integral of the heat transfer over the process 1 to 2, plus the integral, which is equal to the integral of TdS over the process. So not only can I get the net work produced by the cycle from the TS diagram, but I can get the heat transfer. Let me show you what I mean. TS. State 1, here's the path. State 2, this area, the area underneath the TS curve. The area underneath the TS curve is my heat transfer 1 to 2. Okay? This area, which is the integral of TdS, is equal to the heat transfer from 1 to 2. Okay? So the TS diagram, unlike the PV diagram, not only just shows you the work, but it shows you various heat transfers. Let's do an example here and I'll show you how this works. Let's do a little example and I'll show you how this works. Let's do a little example. Let's say I have 2 cycles. Here's one, and here is the second cycle. These are both TS diagrams. So let's say, here's my first cycle. There's my first cycle, okay? So the cycle is going in this direction. There's my first cycle. And here's my second cycle. Lower on the TS diagram. Lower on the TS diagram. Let's compare the works over the cycle. So this is cycle A, and this is cycle B. Well, the work is represented, the cycle work is represented by the area bound by the TS curve. So this equals work cycle for cycle A, and this equals the cycle work for cycle B. Notice these triangles are approximately the same shape. They are the same shape. So I have the cycle work for cycle A equals the cycle work for cycle B. Okay? Same shape and size. Okay? Same area bound by the TS curve over the cycle. Same works. Let's compare the heat transfer into the system over the cycle. So let's compare QH. Let's see here, what's QH for cycle A? Where's the heat being added? Where's the heat being added in my cycle? Well, notice that entropy is increasing. Entropy is increasing on the upper portion of the cycle. So entropy goes up on the upper portion of the cycle. And if entropy goes up, so S is going up, that means Q is being added. And we know that Q is being added from the hot place into my working fluid. So Q high A is actually equal to Q in. Okay, so heat is being added in this part. Q in is being added in this portion of the cycle. Now, as we can see over here, the area underneath the TS curve represents the heat transfer for an internally reversible process. The area underneath the TS curve represents the heat transfer into the system. So this blue area is my heat transfer into my system. So this blue area represents my Q in or my Q high, if you like, for cycle A. Okay, because entropy is increasing from this point to this point. Everywhere else, from here to here and from here to here, it's declining. So the heat rejection is the area underneath the bottom part of the cycle. Heat addition occurs at the top. Okay, so I got a pretty big area. How about this one? The heat addition, QN B, if you like, that's Q low B. That's represented by this area. So the heat is being added on the top portion of the cycle. The cycle is going in the clockwise direction. So that's where the heat is being added, okay? So Q in is represented by that area. Which cycle has a greater heat input? This part, the cycle, cycle A. So note, Q in A is greater than Q in B. Areas different. And what areas am I referring to? I'm referring to the crosshatch areas, okay? Okay, let's calculate the efficiency. Let's compare the efficiency. So remember, efficiency for a heat engine is the work over the cycle divided by the heat input from the high temperature place. Now in our case, the works are the same, but the heat transfers are different. Cycle A has a greater heat transfer than cycle B. So the denominator is larger for cycle A than cycle B. So that means the efficiency of cycle A is less than the efficiency of cycle B. And that's because the heat transfer is greater into the system for cycle A than cycle B, okay? So this is kind of cute. This means I can envision all sorts of cycles. All I got to do is draw them, and I can basically eyeball the heat transfer, the work, the efficiency. I can pull everything of interest off of the TS diagram. I can get the heat rejection too. I can not only get the heat I can get the heat transfer in, but I can get the heat transfer out. I can do that too if I want, but usually we're interested only in the heat transfer in. So unlike the PV diagram, which only allows us to calculate boundary work, we can get all sorts of information off the TS diagram. The works over the cycle, which is the area bound by the TS curve over the cycle. But I can also get the heat input. And the heat input corresponds to those sections of the cycle, those processes, where delta S is positive, where entropy is increasing. Okay? This is quite nice. Okay, let's do a numerical example here.